Hello, my dear students, and welcome to this new chapter dealing with the MOSFET. Usually, I mention that the MOSFET is the most important lecture during our course, either in the solid state course in semester one or during this course in the ECE05C for the electronics course. In both courses, we consider the MOSFET as the main building point, block for every electronic analog or digital circuit. That's why I usually ask you to do a lot of effort and make very high concentration in dealing with this lecture. Now, please permit me to start sharing my presentation slides and to start with you the journey for chapter 3 titled by MOSFETs. Okay, so I believe now you can see my presentation slides as well as the pointer. So let's start together, and let's start as usual with a very quick flashback on what we have already learned about the MOSFET in the solid state electronic course. MOSFET generally is a four-terminal device. We have a substrate. So for example, this is an N-channel MOSFET. That's why we have a P substrate. We have a source and drain with an N doping. We have the oxide layer covering the gate, and we have the metal contact. So we have a body contact connected to the substrate. We have the source connected to a terminal connected to the source. We have a terminal connected to the drain, and we have a metal above the oxide indicating the gate. So this is a four-terminal device. However, in maybe 99.9% of the cases, especially in this course, we will deal with the MOSFET as a three-terminal device, so we can just ignore the effect of the body, or you can say that the body is grounded all the time or connected to the source all the time. So we are dealing with this MOSFET as a three-terminal device. Okay, so if you remember, whenever we study MOSFET one semester ago, we have mentioned that if you start to plot an energy band diagram for this NPN junction, indicating the drain, the channel, or the channel region, and the source, you will find that the majority carriers, I mean the electrons in the source or the electrons in the drain, are not able to move to other sides. This is simply due to this potential barrier due to the substrate. So the first step in order to allow electrons to move from the source to the drain or from the drain to the source is simply to add a positive voltage to the gate. This positive voltage will act to invert this channel. That's why we call it a channel. Invert this region, which is a channel, so that it can connect the source to the drain and the electrons can move from the source to the drain. Simply the voltage needed in order to create or to invert this region, this channel, is what we call the threshold voltage. So the threshold voltage is the minimum voltage needed on the gate in order to connect the source to the drain. Now you have a source connected to the drain. The two islands are now connected. So the next step is that you need electrons to move from here to there. And to do so, you need some sort of motivation. That's why we add this VD, or the drain voltage. The drain voltage will act to attract electron from the source. So this electron will start to move through the channel to reach the drain, and then you have electrons moving, and then you have a current. This is simply how the MOSFET works. Whenever you start to increase this VD, that simply means that you increase the attraction force. So more and more electrons were going to move from the source to the drain. That's why you have a higher current. So in a very simple manner, the higher the VD, the higher the ID. However, we have studied together that at a certain voltage, which we call the saturation voltage, a phenomena called the pinch-off starts to appear. This phenomena is simply observed here, where the width of the channel tends to be 0, and this called what we call the saturation region. So whenever we have an IV curve for a diode, and here what I mean by IV curve is plotting the VDS, or the voltage applied to the drain with respect to the source, versus the ID, or the current flowing from the source to the drain. So whenever we have such a curve, you can find that we have three regions of operation. The first is what we call the cutoff region, where the voltage applied to the gate is still below the threshold voltage. In this case, no current is conducted in the MOSFET theoretically. Then we have another two regions of operation. If the voltage on the drain is still below the saturation voltage, then the higher the voltage, the higher the current, which is this triode region, as you can see. So this region is defined where the VDS is still below the VDS SAT, which is VGS minus V threshold. However, once the VDS reaches the VDS SAT, which is VGS minus V threshold, then we start to enter what's called the saturation region, as you can see. If you return back to the solid state lecture, you will find that we call it the ideal IV curve, because here we assume that the resistance is infinity. Whenever you have an horizontal straight line, then the resistance is infinity. However, in the realistic curves, we have some R output or some slope to indicate the resistance of the output, or the resistance of the saturation region. Okay, so this is how the MOSFET operates. This is a very quick manner. In this course, as I mentioned, we will deal with the MOSFET as a circuit element. We no longer need to study in details these schematics and this energy band diagram. Now we have this MOSFET, this N-channel MOSFET, as just a circuit schematic. By the way, this maybe will be illustrated later on, that we have an N-channel MOSFET and a P-channel MOSFET. This can be indicated by the direction of the arrow. So whenever the arrow is outgoing from the source, this is an N channel. If the arrow is ingoing to the source, then this is a P channel. I will demonstrate this later on in the presentation. So this is the theory of operation. Now we have also other characteristic curve, which is not as famous as this one, but is also important, which is the VGS versus ID. So please take care. Here is VD, or the drain voltage, versus the drain current. The drain voltage is this voltage, the voltage applied to the drain, and the drain current is simply the current flowing from the source to the drain. So whenever electrons flow from the source to the drain, that means that current is flowing from the drain to the source, because current is defined as the inverse direction of the flowing of electrons. So this is the first characteristics, to have the VD versus the ID. Then the second type of characteristics is to have the VGS versus ID. So now the x-axis includes the VG, or the voltage applied to the gate, and the y-axis still includes the current flowing from the source to the drain. So this is the characteristics. As you can see, you can detect this V threshold here. So below V threshold, you don't have a current. Whenever you have voltage on the gate greater than V threshold, then current starts to increase in this manner. So this is what we call the ID VGS characteristics. Also, there is another point, this is just for your information. I will not ask you about it in the final exam, which is this region. Let me highlight it. This region. This region, what we call the sub-threshold region, or whenever the gate voltage is below the threshold voltage. Theoretically speaking, in our courses, we will deal with this region as that in this region, the current is equal to 0. As you can see here the current is equal to 0. Also, you can, if we turn back one slide backward here, the current also is equal to 0. So whenever the voltage on the gate is below the V threshold, then the current is equal to 0. However, realistically, this is not true. Realistically, in the realistic MOSFET, we have what's called the sub-threshold variation, or the sub-threshold voltage, or the sub-threshold swing. So this is the voltage. As you can see, the current is very, very low. As you can see from the order of magnitude, this is by the way, this is a log scale. So you can see that the current is very, very low, but it exists. It's not absolute 0. Again, this is just for your information. Okay, so now let's turn back to the IV characteristic curve of a dot. As I mentioned, we have two regions. We have three. The cutoff region is the region where the voltage of the gate is below the V threshold. But whenever the voltage on the gate is above V threshold, I mean the transistor is on. So we call the transistor is on when the voltage on the gate is above the V threshold. So whenever the transistor is on, then we have two regions, what we call the triode region, and this is defined where the VDS is still small, below VGS minus V threshold, and what we call the saturation region, which the case where VDS is greater than VGS minus V threshold. So these are the two regions. Okay, as you can see in this triode region, we have actually two variations. In this region, in the beginning of the triad region, it seems like that the voltage and the current are almost linear here. However, by increasing the VDS somehow, as a curvature here starts to appear, as you can see. So now what we are seeking for is to write an equation for the current flowing in the MOSFET. Of course, you are not requested for any derivations for this equation. You just need to know, you just need to memorize this equation, and we will use this equation while solving circuits related to us. So generally speaking, if we would like to write an equation that express the voltage and the current in the saturation region, the equation will look like this. So this is the general equation for the current flowing in the triad region. Let's examine the equation. This is ID, which is represented in the y-axis, equals Kn dash. Kn dash is a material parameter. It depends on the type of the material you use. For example, you are using silicon or whatever. It depends on the thickness of the oxide. If you remember the oxide layer, so this is the oxide layer, so the thickness of the oxide, or this stuff. In our course, all the time Kn dash will be given as will be set as a given. So I will give you an Kn dash. W over L, which is again a dimensional parameter. W is the width of the channel, and L is the length of the channel. Again, these will be given. So Kn dash WL for a certain MOSFET, we can say that Kn dash WL over L is a constant, because of course for a certain MOSFET you will have a certain material with a certain dimension. Then we have VGS minus V threshold. VGS, of course, the voltage applies to the gate, and V threshold is the threshold voltage, multiplied by VDS minus VDS square over 2. So this equation represents the current flowing in the triad region. As I mentioned, this equation consists of two components. A linear component. Here, as you can see in this component, ID is linearly proportional to VDS, which is this region. And a quadratic component, which is this one. As you can see here, ID is proportional to the square of the VDS. In sometimes, when VDS is very small, I mean, whenever you are working in this region, I mean, VDS is much smaller than VGS minus V threshold, you can approximate it in this manner. So you can simply say that VDS square over 2 is relatively small compared to this term. So I just ignore this VDS square over 2, and then I just use it in a very easy linear manner. This is just to make mathematically life easy, because this is a quadratic equation. However, this is a linear equation. Of course, it is usually easy for you to deal with a linear equation rather than to deal with a quadratic equation. So this is a valid approximation whenever this term, which is VGS minus V threshold times VDS, is much greater than this term, which is VDS square over 2. Okay, perfect. As this is a linear relation between the voltage and the current, we all know that the most famous linear relation between a voltage and the current is the resistance. V equals I times R. So if we make it in this manner, we can calculate what we can say the RDS, or the resistance, the drain source resistance, or what I believe it's better to say, this is the triad resistance. So this is simply when I did V over I. So I have all these terms, 1 over these terms. So it's Kn dash W over L, VGS minus V threshold, all power minus 1. So this represents the resistance seen by the current whenever the electron starts to move from the source to the drain in the triad region. So this is the first equation. Of course, here we apply this linear approximation when we ignore this VDS square over 2 term. Perfect. So now, what about the other region? We still have one more region, which is the saturation region. How we can represent current in the saturation region? First of all, as you can see in this ideal MOSFET, you can say that the current is constant with respect to VDS. So that means that the current is independent on VDS. So whenever you're increasing the VDS, the current is still the same value. That's why the equation looks like this. It's Kn dash W over 2L VGS minus V threshold all square. As you can see now in this equation, we don't have VDS, or ID is not a function in a VDS. This is simply because ID is a constant. So this is the saturation region. So now we have the ability to describe both region in a mathematical form, either the triad region, which can be described in an exact form or in an approximated form by ignoring this VDS square over 2, or the saturation region, which can be expressed in this form, which is again independent on VDS. Okay, let's go to the next step. Okay, so this is the equation representing the current flowing in the saturation region for a MOSFET. Now, can we manage this? We have said that, or we said that this region is represented in a form of a resistance, if you remember. So you can represent the MOSFET in the triad region as a resistance, where the resistance value is with this value Kn dash W over L VGS minus V threshold all power minus 1. Now, how we can represent this value, this region? It's a constant current. So if you remember, if you recall your circuit's memory, you will find that this is a current source, because the definition of the current source is that the source that supply a constant current. But this is not only a current source. This is what we call, my dear students, a voltage dependent current source, because the value of the current here is dependent on VGS, which is an input in our system, in our transistor. I believe you already see this circuit schematic before in your circuits module. So this is what we call a voltage dependent current source. A voltage dependent current source that's depend on the voltage coming from the gate. So whenever the voltage on the gate increase, whenever the current flowing in this current source increase. This is the case. Okay, perfect. There is a very important parameter here, which is again something somehow advanced. It may be somehow out of the scope of this course, and most probably you will not use it till you reach year 4 and you study what's called the VLSI course, which what we call the channel modulation. What is the channel modulation? Let me return back to this bench of slide. So this is the point at which a pinch off starts to appear, whenever the VDS is equals to VGS minus V threshold. Once you start to increase this VDS to be greater than VDS SAT, then what happens simply, if you go back to the solid state electronics course, that these pinch off points will start to move toward left. This simply means that with a very high saturation stage, I mean, when in this region, for example, when VDS is relatively high, the channel length starts to decrease. So this is the original channel length, this is the drain, but due to the increase of the VDS greater than VDS SAT, due to the pinch off point starts to move toward left, towards the source, and the effective channel length decrease. So this new L is smaller than the original L in the channel. So that's introduce another parameter, that this L is not a constant value. Herein, in the triad region, it's a constant, because in the triad region, the channel length is not affected. But herein, the channel length is affected. And this is what we call the channel length modulation, by the way. Again, this is somehow an advanced topic that maybe will be considered later on in other courses. But let's go another round due to the saturation, or in the saturation region. If you remember, I told you that this is the realistic IV curve for a MOSFET. This is a realistic curve because here we assume that the resistance is infinity. That's why we have a constant horizontal line. But realistically speaking, we have such an IV curve. So there is some sort of a resistance here, some sort of a slope here. So in order to include this slope in the model, what we are going to do is just to add a resistance. So as you can see, it's typically the same as the ideal model, but with what's called an R out. R out simply is the slope, or 1 over the slope of this line. So whenever this is a horizontal line, the slope is 0, 1 over the slope is infinity. So this is an open circuit. Once there is a slope, then this R node starts to appear, as you can see. So this is the realistic model for the saturation in for the MOSFET in the saturation region. Then we have, as we mentioned in the solid state, or as we mentioned in the beginning of this lecture, we have two types of MOSFETs. We have what's called an N-channel MOSFET. It's an N channel because the source and drain are N, so we are connecting here the channel as an N. And we have what's called the P channel MOSFET. So these are the schematic diagrams for both the N channel MOSFET and the P channel MOSFET. Usually in this course, maybe or in this lecture, I mean, most probably I will give you the equation in terms of the N channel MOSFET. However, maybe in your tutorial problem, you will solve some questions regarding the P channel. It's typically the same, just the reverse or the counter polarity. So for example, in the case of the N channel MOSFET, we need to have a gate voltage with a positive, which is a positive voltage. However, in the P channel, we insert a negative gate voltage in order to accumulate holes here or to invert this region to be a P type. So it's typically the same concept with a different polarity. Now, this is a termination for part number one. It's something related to refreshing our knowledge with the MOSFET and also to go through the IV characteristic curves. In the second part, which is the most important part, especially for those who are targeting to get high marks in the exam, we are going to go to solving circuits with MOSFETs. We are going to solve circuits in a DC, what we call the DC analysis, and also in what we call the AC analysis. So please, first, thank you for your consideration, and please keep tracking these videos to go to ahead to the second part of this lecture dealing with the MOSFETs. Circuit analysis. Thank you very much for your consideration, and see you بإذن الله next lecture. Thank you very much.